Hi everyone, I am Pradeepan Kadiravelu from Emory University. Today I am presenting our paper Latency Sensitive Web Service Workflows, a case for a software-defined internet. This work was completed last year during my PhD at UC Leuven and INESC ID Lisboa. The internet landscape has been growing in a promising manner for the past few decades. The demand for bandwidth keeps increasing. At the same time, its pricing keeps decreasing. The invent of the cloud computing is remarkable for the internet. The cloud ecosystem consists of several service providers. These service providers manage the infrastructure, platform, or applications and offer them to the tenants following a pay-as-you-go model. Tenants, the third-party end users, consume these services. The cloud ecosystem helps the users innovate without having to configure or manage their own infrastructure or third-party software. Major cloud providers, such as Amazon Web Services, typically manage their own global backbone network. They avoid having to route their cloud traffic, including those between their regions, through the public internet. Their geographical presence keeps increasing with the number of regions, availability zones, and points of presence. By using their own well-provisioned network exclusively, each major cloud provider manages to offer low-latency network links among their VMs. These advances in the cloud ecosystem further improve the user experience of Internet services. However, there are several challenges that must be addressed in the Internet ecosystem to make it fair for every user, regardless of their region. First, the developing Internet regions rely on long-haul Internet links to the major Internet hubs to connect with the other regions. Consequently, developing Internet regions also suffer from high latency. This state of affairs makes them inefficient for latency-sensitive web applications such as online gaming, high-frequency trading, and remote surgery. Second, the connectivity providers provide limited control and flexibility to the end users. The end users cannot choose their network paths according to their policies. Third, the border gateway protocol. The standard exterior gateway protocol of the Internet is not optimized for performance. There is no guarantee that a latency sensitive workflow can leverage the best Internet paths in its routing. As a demonstration, let's consider the end-to-end latency across several countries. RIPE Atlas is an Internet measurement network consisting of several small network devices known as probes scattered across the globe. We used RIPE Atlas probes to send data from several countries to probes in Colombia. The figure shows the latency measurements from the Internet regions in sending data to Colombia. It indicates the average of hundreds of ping measurements with an hour interval during a 24-hour period. We highlight the latency from the Reunion Island as well as Mauritius to Colombia. Despite their proximity, Reunion has a much lower internet latency compared to that of Mauritius. Also, we note that despite the geographical proximity, many neighbor countries and regions in South America did not demonstrate a lower latency to Colombia. This highlights the inequality of the Internet architecture, which follows a hub and spoke topology, with major Internet regions acting as the hubs. This shows the differences in Internet performance, even between the neighbor countries. There have been several attempts to improve the networks in terms of control, reusability, and interoperability. Network softwarization refers to a set of such approaches. Network softwarization makes networks programmable through software constructs by separating the networks into network infrastructure, network control, and network services. Network softwarization aims to improve the network management. However, network softwarization typically limits its focus to a single domain, a network managed by a single provider. A tenant workflow placement across multiple providers requires network awareness beyond a single domain. Software-defined networking and network functions virtualization are two core enablers of network softwarization. SDN unifies the control of the network devices into a logically centralized controller. The controller has a global view and control of the data plane devices, such as network switches and routers. The controller is developed in a high-level programming language, such as Java or Python. Hence, SDN supports efficient management of the networks. NFV, on the other hand, makes network middleboxes such as load balancer and firewall into virtual network functions and lets the users host them on servers. While SDN limits its focus to networks, software-defined systems, or SDS, expands its scope to various aspects such as storage, security, and data center. SDS either extends SDN or follows an approach inspired by SDN. SDS improves the configurability of the environment by separating the mechanisms from the policies. In this paper, we ask whether we can provide a lower latency for remote internet regions by replacing large segments of the internet path with other connectivity options, such as existing private connections between two intermediate nodes. We envision such connections may provide a better control to the end users. We posit that a software-defined systems approach to replacing pathless, the segments of the original path, may provide a better performance or a better control to the end user in routing their own data transfers and latency-sensitive workflow scheduling. We look into software-defined systems to separate the execution from the infrastructure for an interoperable service workflow execution spanning multiple network domains. Cloud-assisted networks refer to the overlay networks that are built on top of the cloud VMs. We consider software-defined systems based on configurable architectures such as cloud-assisted networks. We ask whether an overlay network of cloud VMs can operate as a better connectivity provider. Specifically, such a provider should provide better performance and cost effectiveness than the current connectivity providers, such as internet service providers, enterprise MPLS networks, and transit providers. Furthermore, such cloud-assisted networks should also offer capabilities to host and manage service instances seamlessly across the cloud providers to support inter-cloud workflow compositions. In this paper, we present Software-Defined Internet (SDI), an approach that aims to extend network softwarization to bring more path diversity to the Internet by enabling participants to share their cloud paths and private direct connections with the other participants via an overlay network. SDI aims to be more user-centric. It optimizes existing private connections between two endpoints as part of the internet paths. We envision how an SDI architecture can be realized by sharing network paths and connections between the users, similar to how volunteer computing shares computing resources from volunteers for a complex computational problem. SDI supports a performance-aware web service workflow execution, as these paths can be monitored for their performance by the respective users, compared to relying entirely on the internet for their data transfer and workflow scheduling. To be clear, SDI does not aim to replace the internet architecture. Rather, it tries to complement the internet topology with the available paths by sharing the abundant network resources available at the data centers, clouds, and the edge. Now, we look into the proposed deployment architecture of SDI in a single user site. A user site is an SDI client deployment in a server, a research cluster, or even a laptop of an end user connected with a network router. The deployment consists of a RIPE address probe attached to the network router. The RIPE address probe accumulates RIPE address credits for the time it remains connected online and contributes to the internet measurements of the other RIPE address users. The RIPE address credits can be used to perform internet measurements from the user servers, while also providing internet measurements from the network router to the other probes. However, the RIPE address probe is optional, as credits can be transferred across users for internet measurements. Hosting a probe will provide accurate internet measurement, nevertheless, from the current server, compared to using other probes from the region as an estimate. The figure depicts a sample deployment of SDI at a participating user site. The SDI client is a software deployment at the user server. At the core of the SDI client is the SDI controller that chooses the network path when a data transfer or a workflow is initiated from the user server as the origin. The RIPE address tool's Python client consumes the RIPE address APIs to dynamically measure the internet performance by measuring the latency and traceroute between two endpoints, that is, two RIPE address probes. Thus, the SDI controller leverages the Python client to identify better internet paths in routing the traffic accordingly. Although the RIPE address measures end-to-end latency between two specific probes, such results can be generalized for the regions by running across several probes of the regions. Such calculations, over time, give a current snapshot view of how internet paths are performing at a given point. The SDI registry consists of the participating paths sorted, such that the SDI controller can find the better paths at any given time towards the destination. The scheduler is a software component that is integral in building an SDI overlay by interconnecting with other participating SDI clients at the global scale. It is built as an application layer tool that entirely uses the overlay network. It considers the algorithms and user policies in choosing the paths and enables the overlay to schedule the network flows through the client. Finally, the SDI controller transfers the data or the workflow based on the paths chosen from the registry. The SDI controller matches the policy information from the scheduler as well as the internet measurements from the RIPE address client in its routing decisions. Thus, SDI aims to extend network softwarization to solve the challenges of scheduling web service workflows at an internet scale. SDI aims to replace the large segments of an internet path via alternative connectivity options. In this example, we are considering the cloud-assisted networks for an alternative path. We are sending data from A to Z, first entirely by ISP-based public internet, then via an intermediate point B to use better paths. Let's consider an example of cloud-assisted network. Here we are sending data from Vladivostok to São Paulo. Vladivostok is a user server. São Paulo is a cloud VM, the destination. First, we send data from Vladivostok to São Paulo directly via the public internet. Then, we send data via Tokyo. First from Vladivostok to Tokyo, and then from Tokyo to São Paulo via a cloud-assisted overlay network. So, SDI aims to replace the public internet paths with alternative paths such as cloud-assisted networks and direct connects that the user has more direct control. Furthermore, the vision of SDI is sharing of such paths across the participants of the SDI overlay in the global scale. We prototype SDI with a cloud-assisted network. We then benchmark the SDI throughput against the ISP-based public internet connectivity. We first connect our origin server in Atlanta to the SDI overlay via ISP. Our nearest cloud region is North Virginia. We observe that sending data with SDI via the nearest cloud region can be more stable and offer a higher throughput than sending the data to the destination via the public internet paths entirely. SDI avoids slow long-haul internet links as it covers a significant portion of the data transfer network path. We then benchmark the latency and latency variations of SDI against an ISP. In case of SDI, we connect the origin and destination endpoints with the cloud overlay using two approaches, through the ISP-based public internet and through a simulated direct connect, modeled with realistic latency values. We observe minimal latency variations with SDI. We note that the latency variations in SDI, in most cases, is due to the variations in the ISP's network, connecting the user endpoints with the nearest cloud region. The cloud direct connects promise fixed dedicated connectivity to the end users to connect their on-premise servers to the cloud. Therefore, latency variations are negligible in the cloud direct connects. Consequently, latency variations in SDI with a direct connect represents the actual jitter caused by the SDI overlay. The minimal jitter observed in SDI highlights its suitability for latency-sensitive web applications. We compare SDI with the volunteer computing model, but for networks, we note that the ISPs typically limit their data rate to 100 Mbps, that too often with a cap. SDI can provide a better data rate for end users compared to the ISPs. SDI can provide a low latency overlay network, workflows routed entirely through the application layer. There are a few companies that follow an approach similar to SDI. Voxility operates as an alternative to transit providers using an overlay network built on top of its global infrastructure. Teradeon offers internet fast lanes for software as a service providers. We observe that software-defined systems, such as cloud-assisted networks, can be exploited as a connectivity provider. There are also community network initiatives that aim to bring internet to remote regions without relying on ISPs. They limit their focus to a small region, which is more feasible. SDI expands this approach to the internet scale, leveraging the internet measurements and network softwarization. In summary, SDI is an overlay network that does not own the infrastructure but shares the networks from participants to replace the internet paths. We consider cloud-assisted networks and direct connections between user servers as two examples. SDI offers low latency end-to-end data transfer through its overlay network, a network constructed from the participants' network resources. The internet measurement tools are a crucial part of the SDI ecosystem. We use RIPE Atlas. However, it can be replaced by any similar internet measurement tool. We end the presentation with our future work on practical challenges and potential to implement and deploy SDI on a global scale. Thank you for your attention. Now, I open the session for questions.